So students will study today isomerism. Now in the regular classes you have studied isomerism is having two, that is structural and stereo. Alright. Here structural isomerism is also called as constitutional isomerism. It is also known as constitutional isomerism is also called as. Now why constitutional? Constitutional isomerism is known as, for that particular purpose, listen carefully, when there is difference in the connectivity of the atom. When there is difference in the connectivity of atom. Alright, so hence it is called as constitutional. You will see in structural isomerism, what you will find? There is a difference in the connectivity of the atoms. You will say how difference in connectivity means? For example, let us say you have studied this one in the regular classes, C4H10O. It shows two kinds of functional isomerism, that is C2H5OH. I am writing in this way. Alright, rather let me simplify it much more, then better. That is, this one is CH3, this one is CH2, and this is OH. Fine. We can also write it as, that is CC and between O, then CC. So here it is CH3, then it is CH2, then it is CH2, and this is your CH3. We can say that. So what you see, now see the meaning of the word connectivity means what? Here the oxygen atom is connected one bond to carbon, another bond to hydrogen. Here the oxygen atom is connected both the bond to both the carbon atoms. Here both the bond of oxygen atom is connected to the carbon atoms. Here both the bond is connected to carbon as well as hydrogen. So the connectivity is different. So in this way, for that particular reason, you will find this is known as constitutional isomerism. The connectivity differs. Alright, for that reason it's called as. Now it's not that, sir, you said about functional, what about chain, positional, metamers? You will find there's differences in it. You will find there's a differences. In all the isomers you may not find it out, but in definitely you will find it out. Like positional isomers you will find it out. Functional you will find it out. Metamers, ring chain, tautomers you will find it out. Understood? Just explained you the word that why it is called as constitutional. Alright, as I said you, it may or may not be for all isomers, but it is true for some isomers or not. For that reason it is called constitutional. Next, stereo isomers divided into conformational and configurational isomers. Conformational and configurational isomers. Conformational we don't have conformational any other branches. But configurational isomers we are having geometrical or cis trans isomers we have studied already, and optical or enantiomerism it is known as. Got it? So this is coming under stereo, we can say that. So this is the basic, the first we can say. So you will be studying more about it, about conformational, about geometrical, about optical, and of course constitutional you will be studying a little bit. Alright, so altogether a lot of things you are going to study now. Alright, so first let us come to what you can say the constitutional isomerism or structural isomerism. So it is divided into 6 types, you know that: chain, positional, functional, ring chain, metamers, tautomers. Now children, I am going to say you a lot of important points to you. You please note it down, those points. Note it down. First, chain isomerism. In case of chain isomerism, you note down some important points. So, chain isomerism, note down some important points. First point is that is what you find is that the compound, two compounds cannot show chain as well as position isomerism simultaneously. Two compounds means two isomers cannot show chain as well as position, not possible at all. You may try it out and see that the two compounds cannot show chain isomerism as well as position isomerism, it cannot show. Alright, next. Then compounds, that is what you find is that except alkynes. Alright. So that is you are having the isomerism starts from the 4th carbon atoms. I told you the chart if you remember it, that methane has got one isomer, chain isomer, ethane has got one, propane has got one, butane has got two. So what I said you, except alkynes, that is a chain isomers starts from 4th carbon atom, we can say that. From 4th carbon atom the chain isomer starts. Fine. Now next is, this is about chain isomerism, what I have said you, that is it's okay in the regular classes. Then coming to the positional isomerism, you noted the point. Coming to the positional isomerism, wherever it is important points to be said, I am saying you, got it? And wherever we have done it in the regular classes, I am not saying you anything. Got it? That is enough. That is enough what I said in the regular classes. Much more is not there. Now positional isomerism. Now there are certain compounds which does not show positional isomerism. I mean there are certain functional groups you need to remember which does not show positional isomerism. What are those? Aldehydes. Aldehydes, then carboxylic acid, alright, and its derivatives. Derivatives means, and its derivatives means your like acid anhydride derivatives. Acid anhydride, esters, amides, they do not show what you can say functional isomerism. Positional isomerism. Because these all will be always in the first carbon only. It will be. As well as nitriles, C triple bond N. So aldehydes, carboxylic acids and its derivatives and nitriles do not show positional isomerism because all these functional group will be in the first carbon atom. It cannot be anywhere in the middle. Alright, it cannot be anywhere in the middle. Next, the second point is that about positional isomerism. Positional isomerism is not shown by what you can say derivative, alicyclic compound or aromatic compound. Mono substituted or mono derivative, we can say that. Mono substituted means, for example, you are having a alicyclic compound, let us say Cl. Will it show positional isomerism? One is there, na? Only one substituted product is there. Suppose two will be there, then it will have different positions. If one, then how it will be? For example, you are having, suppose a benzene ring is there and you are having here NO2. We can say that. Will it show positional isomerism? For position, it has to be ortho meta para. You have studied. And ortho means first and second. Meta means first and third. Para means first and fourth. So it is di-substituted. It has to be di-substituted. So mono-substituted alicyclic compound and aromatic compound does not show positional isomerism. Noted these points which I am saying you. Next, after that, functional isomerism we are coming. I don't have to say anything about functional isomerism. I have already said you so many things about functional isomerism. Got it? I have talked to you regarding functional isomerism where the functional group is going to differ. Got it? So different kinds of functional isomerism we are having it like aldehydes, ketones and unsaturated alcohol, functional isomerism. Then ethers, alcohols, functional isomerism. Then carboxylic acids, esters, they will show functional isomerism. Then alkenes, then alkenes means dienes and allenes. Got it? As well as alkynes, they will show functional isomerism. Do you know what is this? Dienes. Dienes means suppose we are having 5 carbon atoms. So here one double bond and here one double bond. This is called as a diene. 2 double bond diene. But this 5 carbon atom is there, 5 carbon atoms, and we are having this double bond on the same carbon atom. This is known as what? Allene. Alright? And if you are having a triple bond, let us see. Then this is alkyne. They will show functional isomerism. This is known as a diene, this is known as allene, this is known as alkyne. They will show functional isomerism. Alright, similarly nitro and nitrite. Nitro means NO2. Alright, nitrite means what? ONO. They will show functional isomerism. We can say that. Clear? In this way, many are there. You can make it a chart in this way by yourself and you can find it out that they shows functional isomerism. I will talk to you in the regular classes. Now next is your ring chain isomerism. Already I have studied the ring chain isomerism. Ring chain isomerism, they are having different functional groups, isn't it? One will be ring, closed chain, another will be an open chain. We can say that. Next we have seen that is metamerism. Now note it down here. Metamerism is a special kind of functional isomerism. Positional isomerism. Metamerism is a special kind of positional isomerism. Now how it is positional? For example, pentan 2-one and pentan 3-one. The functional group is differing or not? And it's also a metamers. What I said? Pentan 2-one and pentan 3-one. See here. This is pentan 2-one. I am not writing the hydrogen atom. See here 1 carbon beside this and here 3 carbon. You can see. And here both the side 2 carbons. So what is actually, this is first coming under what? Position. Pentan 2-one and 3-one. Positional. As well as you can see the alkyl group is differing. See it. Alkyl group is differing. If you want, I will put the hydrogen also. What is the problem? CH2, CH2, CH3. Here it is CH3. Here it is CH2. Here it is CH2. Here it is CH3. Now it is clear. So it is pentan 2-one. This is pentan 3-one. So it is also known as special kind of positional isomers. We can say that. Got it? Noted this point. Now we will come to Tautomerism. Now write down, there are some other words for tautomers is there. Tautomerism, I've said in general classes, tautomers are otherwise known as desmotropism or catianotropy. It is also otherwise known as cryptomerism. Right now, cryptomerism, K-R-Y-P-T, cryptomerism, M-I-M-E-R-I-S-M, cryptomerism. It is also called as allotropism. It is known as A-L-L-E-L-O, allotropism, T-R-O-P-I-S-M, tropism. It is also called as metotropy. Metotropy, M-E-T-O, meto, T-R-O-P-Y, metotropy. Or it is also called as dynamic isomerism. Dynamic isomerism. So what are so many words I said you about tautomerism? We can say that. Tautomerism, it is also called as catianotropy or desmotropism. Now I told you it is also called as cryptomerism or allotropism or metotropy or dynamic isomerism. It is also known as. Alright, so you should understand this. Now I have told you already in tautomers, that is there should be function, that is nothing but multiple bond must be there. Alright, multiple bond must be there. Alright, like C double bond O, C triple bond N, C HO, COOH and all these things. And there should be an alpha hydrogen atom. It is also called as acidic hydrogen atom. Alright, alpha hydrogen atom. It is also known as acidic hydrogen atom. Alright, alpha hydrogen atom is known as. Now next is you note it down that which compound does not show tautomers. I have said you last class to you that what you find is that the one which does not have alpha hydrogen atom. Like I gave you the example of benzaldehyde or benzophenone, they do not show. One more you note it down, right? Compounds having quininoid, Q-U-I-N-O-N-O-I-D, quinoid structure does not show tautomerism. Quinoid means this one. This is similar. You can see that. Similar. C double bond O and double bond NH. So this is known as a quinoid structure. They do not show tautomerism. This one. Alright. Compounds having quinoid structure do not show tautomerism. Note. Now during tautomers, what it happens? Number of sigma bonds, pi bonds and lone pair of electrons are always the same in both the tautomers. Note it. In tautomers, when a tautomerism will take place, then what will happen? What is the characteristic? That is what I am saying. Point number one. The number of sigma bonds, pi bonds and lone pair of electrons is same in both the tautomers. Sigma bonds, pi bond and what you can say, lone pair of electrons. Now tautomerism is a chemical phenomena which takes place only in liquid state. Tautomerism is a chemical phenomena which takes place only in liquid state. Tautomerism is catalyzed by both acids as well as with bases. Tautomerism is catalyzed both with acids as well as with bases. I think you have written it. Now, last class I said you that tautomerism is basically keto-enol tautomerism. Now listen carefully here. I said you that it is nothing but intramolecular change. Within the same molecule the change takes place and hence they exist in dynamic equilibrium with each other. Such that one compound is more stable and another compound is less stable. I said you the compound which is less stable in nature, they are said to be as labile form, if you remember it. Now generally what you find is that in this sort of compound like CH3COCH3 and CH3 CH2 CHO, what do you find? That is, this is keto form. This is nothing but we can say that enolic or we can write it here OH and here it is nothing but CH. Of course that is CH2 and let me write here double bond. Okay, double bond. Okay, now it is CH3 enolic. Let me count it. CH3 here 3 bonds, 1 hydrogen. Here also 1, 2, 3 and 1 hydrogen. Correct. So this is your keto form and this is the enolic form. Here the keto form is more stable than the enolic form. Keto form is more stable. Why? Because here the keto form is stable. What you find is that later on you will study it's stable due to resonance. Factor you will be coming. You will study later on. It is stable due to resonance. So the keto form is more stable there. Alright, keto form is more stable here. The keto form is more stable. The reason is also that C double bond O, in resonance you will study. Listen, C double bond O bond is more stronger than this particular bond, C double bond C bond. It is more stronger. C double bond O is more stronger than C double bond C. Stronger means the bond length is here smaller and here the bond length is bigger compared to it. Due to which it is more stronger. So, and more stronger means more stable in nature. More about it you will study in resonance. You will be studying it. But it is not true for in all the cases. You cannot generalize it that keto form will always stable and enol is less stable. Not at all. Suppose if you see this structure, here this is also an enolic form. You can say that enolic form. This is an enolic form. See, in all enolic form. Now this is more stable than the keto form. Keto form is what? This is the keto form. You can say that. This is the keto form. We can say this is a keto form. Here this enolic form is more stable than the keto form. So you cannot generalize it. Let me tell you. Understand this. It differs from compounds to compounds. It differs from, so you cannot mug it up this one. You have to understand it. So how do we come to know? This is being known experimentally. Experimentally we know this particular thing. That the keto form is more stable than enolic form in this case, because here C double bond is more stronger than C double bond C bond, and here the enolic form is more stable than the keto form. We can say that. Clear? Thank you very much.